Hello everyone. Today we will talk about message authentication, and more specifically we will discuss message authentication which are based on block cipher. Before we talk about message authentication based on block cipher, uh, I'd like to discuss a little bit about message authentication. As we already know, to protect our data against passive attack, then what we need is encryption. But if our goal is to protect against active attack, such as message modification, insertion of the message, and so on, we need different approach to do that. And the approach is one of the approaches, I think, is message authentication. So message authentication is a mechanism or service that is used to verify the integrity of messages. A message authentication code requires the use of secret key. So similar to symmetric encryption, here we need to use secret key that is shared between the sender and the receiver. The length of the message here is not fixed, so it can be of variable length. The input here then is the message itself and the secret key. We can call it as KAP. And the output is the authentication code, which is obtained using this function. So what we need to do is to calculate or to apply the function to obtain message authentication code here to the message and to the using the secret key. We will get message authentication code of the message M here. Then after that, both M and MAC M are sent by the sender. But actually there are several varieties for this one, but we will not discuss that in detail here. So both the message and message authentication are sent by the sender. After that, in the receiver side, the receiver will generate the authentication code of the message using the same function here, to verify the message integrity. So that's why the secret key should be shared between the sender and the receiver. KEP should be shared between the sender who needed to apply the function here to the message, and also the receiver who will also apply the same message and the same function here. Okay, so after the receiver generates the authentication code, if the message code is the same as the authentication code generated by the receiver, then it can be assured that the message is not changed. The message is sent from the real sender, and if the message includes sequence number, the order of the message is not changed as well. For the second requirement here, actually we need digital signature as well. So actually in message authentication code itself, this is the requirement. The message is not changed. But if we assume that the shared key, the secret key, are only known by the sender and the receiver, then the second requirement here, the second conclusion here can also be obtained. Okay. This is the illustration of message authentication code. So here the sender will generate the message authentication code using the secret key, and the sender will send the message together with the message authentication code. Sometimes it can also be encrypted. Message authentication code can also be encrypted. And then after that, the receiver will generate the message authentication code using the same key. Then the receiver will compare the message authentication code that's generated by the receiver with the sent message authentication code here. If they are the same, then we can verify the integrity of the message. Okay, now we will discuss message authentication code based on block cipher. So block cipher, especially here the modes of operation in block cipher can be used to generate or to obtain message authentication code. These three are examples in NIST specification. The first one is data authentication algorithm, or DAA. DAA here uses a cipher block chaining or CPC mode of operation, and the block cipher algorithm to be used is DES. And the initial factor is sequence of zeros. The second one is cipher-based message authentication code, or CMAC. In CMAC, we use AES or triple dash, AES and triple dash, and it will be combined with mode of operation of block cipher. The third one, the one that is complete, is counter with cipher block chaining message authentication code, or CCM. CCM here uses AES, and the mode of operation is counter, and it also applies CMAC here. So CMAC in the second specification here is applied in CCM. Why it is complete? Because it provides both authentication and encryption or confidentiality of the message. Okay, first we will discuss data authentication algorithm. Yeah, so as I already mentioned previously, this is actually the use of cipher block chaining, or CPC mode of operation in DES. And the initial factor is a sequence of zeros. DAA is widely used MAC based on DES CPC, again DES CPC. Yeah, so IV is zeros, sequence of zeros, and then for final block we use zero pad. So it will encrypt the message using DES in CPC mode, and the final block will be the message authentication code. So the final block will be sent because that's the message authentication code. Or alternatively, we can also just use, for example, the first 16 bits of the final block, or maybe 32 first bit of the first bits of the final block, and so on. So we can just use m leftmost bits of the final block. However, at the moment, the length of the MAC is considered as too small because since it is too small, since the length is too short, then it is not good for security. As an alternative of this TAA, we can also use message blocks in reverse order. So it's not the original order of the message, but the order is reversed, and then we calculate the message authentication code. So this is the illustration of data authentication algorithm, or DAA. We have here n blocks. Remember that we use 0 paths at the end of for the final block. So this is the first block. It will be encrypted using dash, and the key K. The result will be output of the first block. Then the output will be stored with the second message, the second block of the message. Then encrypted again using the same key. And then the output is O2, the output for the second block. Actually, it doesn't only depend on the second block here, but also depend on the previous block, because we have here chaining using the SOR operation. Yeah, so we continue that until the final block here, we will get ON. This is the message authentication code. It is called data authentication code, and we can just use the first M bits of the final message authentication code here. So the length of the data authentication code can be between 16 to 64 bits. Yeah, that's a data authentication algorithm, or DAA. Okay, but DAA has message size limitation. Also, the length of the message authentication code is too short, even though it is actually widely used in government and industry. One of the way to overcome the problem here related to TAA is by using cipher-based message authentication code, or CMAC. So you can use CMAC here. So CMAC here is adopted by NIC SP 800-38P, and of course the goal is to improve DAA. So this is the general description of the algorithm. So we have here a message with n block cipher. Each has length of p. P here depends on the algorithm, on the encryption algorithm. So for AS, then the length of the block is 128. For triple dash, then the length of the block is 64. But we don't use just dash here. At least we use triple dash. So message will be divided into n blocks, starting from M1 to Mn. This algorithm uses encryption key K of K bits, and key K1 with n bit. So here we use actually two keys. The first one is the encryption key K, and the second one is key K1. Okay, And the length of the key, uh, the length of the encryption key depends on the algorithm to be used. So for AES, the length can be 128, 192, or 256. While for triple dash, we can use either 112 bits or 168 bits of key. Yeah, so again, this is the length of the message, the length of the encryption key here, not this one. Yeah, and this is the how we calculate CMAC. First, for block number 1, M1 here, we do encryption to M1 using the key K. And then for C2, what we do is to sort first, yeah, C1 with the second block. So it is chaining again. Again, we encrypt using the key K, and so on. And at the end of, uh, at the final block, yeah, MN, then we need to short it with CN minus 1. This is the message authentication obtained from the previous block, and sort it with K1. So again, K1 here is not used for encryption, but it is used for the final block there to be short with MN and CN minus 1. Yeah, so that's the final message authentication code. How many bits we want to use? It depends. So here, the tag T here is message authentication code, or the tag will be the most significant bits of CN. The length is T length. So for example, if we want to use only 64 bits for the message authentication code, then we need to use the 64 leftmost bits. 64 leftmost bits, the most significant bits of the final message authentication code. And this is the illustration of CMAC. The first case here is when the message length is integer multiple of block size. So we don't need to do padding here. For this one, then, yeah, as we already discussed in the algorithm, we first encrypt each block here, the first block here, yeah, using the key K, yeah, encrypt, and then sort it with second block, encrypt again with key K, yeah, and so on. Finally, at the final block MN, we sort it with previous result of, we sort it with the result of the previous processing of the block, yeah, message authentication of the previous block, and with K1 as well. Then the result will be again encrypted using the key K, yeah, and what we need to use is the most significant bit, or we can also, of course, use the whole result here. We can also use some of them, but what we need to use is the most significant bit with the length T length here, and that's the tag or message authentication code. If the message length is not an integer multiple of block size, then we need to do padding. This is the padding. 1 followed by zeros. Everything is the same here, except that we need the padding, and we use here K2, not K1, but K2. we will discuss what's K1 and K2 are. Yeah, yeah, this is also the same. So as we already discussed previously, we need K1 and K2 to calculate the final message authentication code. So what is K1? K1 is calculated as follows. First, we need to encrypt n zeros. So the data here consists of only zeros, n zeros. Depends on the algorithm. If we use AES, then we have 128 zeros, sequence of zeros. It will be encrypted using the key K. This is the encryption key. And the result is L. Then, using L, we will get K1. K1 is the multiplication of L with X. What is X? So X here is the first order polynomial. So the multiplication is done on Galois field 2 to the power of n. Yeah, so X here actually is very easy. It is represented by n minus 2 zeros followed by 0, 1. So it's a kind of multiplication, but in this case, what we have is a kind of something like this. Yes. So suppose we have 8 bit. Yeah. So n here is 8. Yeah. For example, of course, if we use AS, then we will have 128 bits. Yeah. So if suppose we have just 8, then X here is like this. 1, 2, 3, 4, 5, 6, 7, 8. So L is multiplied with this one. Actually, it is just a kind of shift left operation. Shift left operation. 1 bit of shift left operation, and then it will be modulo. It will be applied with modulo operation with the final prime integer here. So it will be again multiplication on Galois field 2 to the power of n. So in this case, again, we need to follow the rule of multiplication on Galois field 2 to the power of n. Okay. If the message length is not multiplication of the length of the block, then we need to use K2 instead of K1. And this is also similar. So we first multiply L with X here. This is X. So this is X. And then after that, we again multiply with X. So it is a kind of left shift operation. So again, X square here is the second order polynomial, and it is the element of GF2 to the power of n. If we don't do it one by one here, then what we will get is something like this: 0, 0, 0, zeros, and then 1, 0, 0. So just the left shift of this one, 1 bit left shift of X. Okay, so that's K1 and K2. Okay, now actually we can provide both authentication and encryption. Here we simultaneously protect confidentiality and authenticity of communications. There are several approaches to provide both authentication and encryption to protect confidentiality and authenticity. The first one is this approach, hash then encrypt. So in this case, we need to find the hash code of the message first and then encrypt the hash code. Then MAC, then encrypt. This is the second approach. So in this case, we find or we calculate message authentication, the message authentication code of the message using the key, and then the result will be encrypted using another key. The third one is encrypt then MAC. So for this one, we will have here the encryption of the message, encryption of the message here using K2. It's C, let's see. And then the second one is to find the message authentication code of the result of the encryption. So message authentication code of the ciphertext here. So that's T. So we'll have two elements here. The message, the ciphertext itself, and the second one is the message authentication of code of the ciphertext. The fourth approach is encrypt and MAC. Encrypt and MAC. So here we find the ciphertext of the message, and then we calculate the message authentication code of the original message. So we don't use the ciphertext here, but we use the plain text. Let's encrypt and MAC. Different from encrypt then MAC. Encrypt then MAC. Those are the approaches that can be used when we need to protect both confidentiality and authenticity. And decryption verification is just using the reverse. One of the standardized algorithm to do that is by using this one. So it is in NICS specification as well, CCM, counter with cipher blockchaining message authentication code. So the name is very long here. Counter with cipher blockchaining message authentication code. Cipher blockchaining message authentication code itself is CMAC actually. CMAC. But here we still use counter. So this is one of the authenticated encryption mode. We have here, if the application needs both authentication and encryption, then we can use this algorithm, CCM. The elements of CCM are like this. The first one is encryption algorithm to be used, AES. Then we also make use of counter modes of operation, and we also use CMAC authentication algorithm. CMAC authentication algorithm is the one that we already discussed previously. And then there is one key here, K. It is used for both encryption and authentication using CMAC. And it is specified in NIST standard SP 838C for Wi-Fi. And this is actually one of the approaches for encrypt and MAC. Encrypt and MAC. That's the fourth approach here to provide confidentiality and authentication. This is the algorithm. The input here consists of three components. The first one is data to be authenticated and encrypted, which is a plain text consisting of blocks. This data is referred to as P. So we have P here, plain text. Then we have associated data A, which will be authenticated but not encrypted. An example of such kind of data is the protocol which needs to be sent. So that's A. So we have P, the plain text, and then associated data A, it must be authenticated. And the last one is nonce, N. This is a unique value that is different for every instance during the lifetime of a protocol association and is intended to prevent replay attacks. So we need to specify the nonce as well, and it must be unique value for each instance. It cannot be reused. Yeah, so we have P, plain text, associated data A, and then nonce, N. The plain text must be authenticated and encrypted. The associated data needs to be authenticated, but not encrypted. Yeah, since CCM provides both authentication and encryption, then we have two processes here, authentication process and encryption process. And we use just one key for both authentication and encryption. First, we will discuss authentication process. For the authentication process here, the input is N, A, and P, nonce, associated data, and plain text. Remember, plain text needs to be authenticated and encrypted, while associated data just need to be authenticated. Yeah, the input here is formatted as sequence of blocks from P0 to PR. The first block contains nonce and several formatting bits indicating the length of N, A, and P. So nonce is in the first block, but it will also followed by several formatting bits indicating the length of N, A, and P. It is followed by 0 or more blocks containing A. So A is placed after N, then followed by 0 or more blocks containing P. P is on the rightmost place. This block sequence is the input of CMAC algorithm. So we will have something like this. Nonce should be associated data here, and then plain text. They will be divided into R blocks, and we apply CMAC. We apply CMAC here using the key K. So as we already discussed previously, CMAC here is used to get, or is applied to get the message authentication code as a tag here. So that's authentication process. This is the authentication algorithm. Basically, we use CMAC here. So we have here blocks, R blocks, P0 to PR. First, we encrypt key P0 here using the key K. We get Y0. Then we do iterations here from I equals to 1 to R. PI is sort with yi minus 1, sort with the previous message, the message authentication of the previous block, using the key, encrypted. And then after that, we need to use TLAN, most significant bit of YR, the last message authentication code the final message authentication code. What about encryption process? For the encryption process, we need to use counter modes of operation. Yeah. So sequence of counters are generated here, which must be independent of nonce. Then authentication tag is encrypted. So the tag is encrypted in counter mode using single counter, which is called counter 0. So we encrypt the authentication tag, the one that we already get here, tag here, will be encrypted, and we use counter 0 to encrypt to encrypt the authentication tag. Counter 0 is the first counter. Okay. Yeah, other counters are used to encrypt the plain text. Yeah. The encrypted plain text is concatenated with the encrypted tag to form ciphertext output. Yeah, this is the illustration. So here, as we can see, we have the tag here, message authentication code. It will be encrypted using counter number 0, the first counter here. So as we already discussed before midterm, counter 0 here is encrypted using the key, and then it will be sorted with the tag. Will be sorted with the tag. That it becomes the encrypted tag. Encrypted tag here. For the plain text, of course, we need to divide them into blocks. And then for each block, we need to apply similar operation here, but we use counter 1 for the first block, then counter 2 for the second block, and so on until the final block. Yeah, so we will have here the ciphertext of the plain text and the ciphertext of the authentic of the message authentication code. It will be the ciphertext, the whole ciphertext. And this is the encryption algorithm. Basically, yeah, this is the use of counter, the one that we already discussed. We do this iteration. Counter J is used to encrypt block number J using the key K. And then, actually, using this algorithm, what we do is to generate the key stream first. This is the key stream. The key stream is the result of the encryption of the counter with the key. So we will have S1, S2, and so on until Sm. If we divide the plain text into M blocks. Yeah, so these are the key stream. Yeah. Then the key stream will be short with the plain text here. And then it will be concatenated with the encrypted tag. This is the encrypted tag. So this is the key stream produced by counter number 0, sort with the message authentication code. The whole sequence here will form the ciphertext, which is sent to the receiver. Yeah. For decryption and verification, the input is ciphertext, nonce and associated data, the key, and the initial counter. Yeah, if the length of the ciphertext is less than the length of the message authentication code, then return invalid. Then for the decryption here, we generate the key string first, counter number 0 to counter number m. We will get S0 to SM, yeah, but for decrypting ciphertext, then we use S1 to SM. S0 is used to decrypt the encrypted message authentication code. Yeah, S1 to SM, and then P is just using the sort operation between the ciphertext and the key string. While the tag message authentication code here is obtained by sorting the key string for counter number 0, which is S0, with the encrypted message authentication code. This one. Yeah, okay, so we will get P and T as the output of this process. And for the verification, we produce here sequence of blocks P0 to PR. P0 to PR consists of the nonce and then associated data and the plain text. And then after that, we generate the message authentication code using CMAC algorithm here. So we will get message authentication code that is generated by the receiver here. This one, MSPYR. This is the message authentication code generated by the receiver using this algorithm. So at the rth iteration, we will get YR. If the tag produced here is not the same as the message authentication code generated or calculated by the receiver, then the message is invalid. It means that it is already modified during the transmission. But if they are the same, then the message is valid. Return P. Okay. Yeah. Several characteristics of CCM. You can see it is a complex algorithm because we need two processes for plain text, for the generation of MAC value, and for the encryption. And there is trade-off between the length of nonce and tag, and the key is used twice to generate tag and to encrypt the text and plain text. Yeah, but it provides high level of security because it provides both authentication and encryption. Yeah. Okay. The slides are obtained from the book by William Stallings, Cryptography and Network Security. That's it, I think, for the discussion of message authentication code based on Block Cipher. Thank you for watching, and we will meet in the next video.